Given the finite charged wire from 0,6 to 3,0 carrying a charge density of 3 coulombs per meter, find the electric field at the origin. So let's get started by interpreting the problem statement. This straight wire will be joining the 2 points 0,6 and 3,0. Now we want to find the electric field at the origin. Now because this isn't a point charge, we will have to integrate over this entire wire in order to find the vector quantity of the electric field at the origin. Let's start by considering a small differential charge dq. Now charge is in units of coulombs, however we are given only charge density in coulombs per meter. This means that we will have to multiply this charge density, lambda, by a small differential length dl, which is the same length of the differential charge dq. Thus, dq equals lambda times dl. So now we want to draw a vector from dq that passes through the origin we will call dE. This is the effect that this differential charge has on the origin. Now that we have a basic understanding of the problem, we can begin to write Coulomb's law for an electric field. So this law states that the electric field of a charge is proportional to the total charge q of the object over the distance or radius r squared, which is the distance of the desired point where we want to measure the electric field and the charge, once again squared. Now it's also crucial to remember that the electric field is a vector quantity. That means that we have to multiply by a unit vector n hat. A unit vector is a distance vector divided by its magnitude. But which way does this vector point? I'll get into more detail about this when we find the unit vector n hat, but briefly stated, because the wire is positively charged, then all electric field lines point away from this charge, so therefore the distance vector will be from the wire to the origin. Now as I stated previously, we will have to integrate over the entire charge of the wire in order to find the effect that each little piece of the wire has on the origin. But before we write the electric field equation in integral form, let's first consider the effect that this small differential charge dq has on the origin. Now again, we will be adding up every single little piece of this wire and its effect it has on the origin. So now we have these three terms, dl, r, and n hat. Let's first analyze the radius r. This is the distance between the wire and the origin. So using Pythagorean's theorem, we can break this distance into its x and y components. Now using the distance equation, which is just Pythagorean's theorem, we can take the distance from the origin to the wire. Since the point we want to find the electric field is at the origin, 0, 0, then x naught and y naught is just 0. Therefore, we can simplify this equation to be r equals the square root of x squared plus y squared. The only thing is we have two variables here, so we need to think of a way to put this equation into terms of one variable. Now the simplest answer is to put everything in terms of x. This is the most commonly used variable when integrating. So in order to put y in terms of x, we need to find the relationship between x and y. Well, this wire is just a straight line, which means it's linear. So we can go ahead and write the standard form for a line, y equals mx plus b. We know m is the slope, which is rise over run. The wire rises a total length of 6 and runs a total length of 3, with the y-intercept b equal to 6. Now notice that as x increases, y decreases. This means that we need to include a negative sign into the equation. So y simplifies to negative 2x plus 6, which we can then substitute in for y. Now in order to get r squared, we square both sides of the equation. This cancels out the square root, and thus we have r squared. So there we go. We derived one of the three components of the electric field equation at the origin. Now I want to take a look at the term dl in our differential electric field equation. dl is a small differential length of the wire that has the same length of the differential charge dq. So I will draw dl in purple as not to be confused with dq. So once again, using Pythagorean theorem, we will break the small differential length in terms of the axes dx and dy, and thus dl equals the square root of dx squared plus dy squared. Now recall that when we found the radius, we put everything in terms of x. So to adhere to this consistency, we will write dl in terms of dx. So this means that we want to pull dx out of this radical. So let's start by factoring out a dx. Now we have dx squared times the quantity of 1 plus dy squared over dx squared. So let's simplify this further and pull dx squared out of the radical, which yields just dx. Now we have this very peculiar term, dy over dx. Now you must be thinking to yourself, hey, that looks an awful lot like a derivative. And you're right, it is. It's the derivative of y with respect to x. Now we know that the derivative of a line equation is just the slope. In this case, m equals negative 2. This means that the derivative of y with respect to x is just negative 2. So plugging this in, we get dl equals dx times the square root of 5. So there we have it, 2 out of the 3 components of the electric field at the origin. Now let's look at the final piece of the puzzle, n hat. Now recall that I said because this wire is positively charged, then our unit vector n hat will be pointing from the line to the origin, because electric field lines always point away from positively charged objects. So now let's consider a distance vector or radius vector, r. Now this will be extremely similar to when we found the radius, but we will put this in vector notation regarding x and y components. Now the trick here is, when finding the components of the vector, it will always be final minus initial. This represents the distance vector from the line to the origin. So for the x component, we will have the origin 0 minus the x component of the line, and then we will do the same for the y component. Now we previously found y to be negative 2x plus 6, so we can go ahead and substitute this for y, and we finally have n hat as the distance vector over its magnitude. Finally, we have derived all 3 components for the electric field equation at the origin. Now we can go ahead and integrate both sides of this equation. So the integral of dE is just e. And recall that the domain of this function, y equals negative 2x plus 6, is from 0 to 3. So because our variable of integration is x, x only goes from 0 to 3. So we integrate the right side of the equation from 0 to 3. Now below, I simplified the electric field by breaking it into its x and y components, and doing a little bit of algebra along the way. And below that, we have our final answer. And if you want to go ahead and integrate this on your own using a calculator, I highly suggest it. Also, I highly suggest that you try to do this problem on your own using a different function that's not y equals negative 2x plus 3. And if you're really looking for a challenge, try to represent the wire as a function that's nonlinear, such as exponentials, sines, cosines, whatnot. And once again, the written solution for this problem is in the description.